Today's pre-calculus notes are on sequences and series, so let's just start by talking about what these words mean. Well, a sequence is like a list of numbers. So a sequence is just a list of terms. And I suppose it doesn't have to be numbers, just a list of any terms. Like if you had something like 1, 3, 5, 7, 9, etc., etc. There's a sequence. What a series is a sum of a sequence. So in this next unit, we're going to look at different lists of numbers mainly, and in some cases we'll have to add up the numbers in that list. So let's take a look at a couple, actually 5 different formulas that'll be handy to us. So first formula. Well, first thing before we get started, you'll notice some of these formulas talk about arithmetic sequences and some talk about geometric sequences. An arithmetic sequence is a sequence like the one I wrote on the previous page, a sequence in which every term increases by the same or decreases by the same amount. Now this amount, like in this case it goes up 2 every time, is often denoted with the letter n. So if in this sequence we see, often denoted with the letter D, my apologies, letter D. So this common difference is the letter D. N is the number of terms. So this is saying to find the nth term, perhaps the 10th term in this sequence, you take the common difference, which in this case is 2, times n, the number of terms, which is 10, plus a sub 0. A sub 0 is the 0th term. So if you're going backwards 1 term, that would be a sub 0. And this formula is a lot like y equals mx plus b. To find the nth term, it is the common difference, which is like the slope, times the number of x's plus b, which is like the 0th term. Now if we wanted to add that list together, we could take the number of terms divided by 2 times in parentheses the first term plus the last term. So if you pair these up, first term plus the last term, first term plus the last term, you always get some common amount. And you take the number of terms divided by 2 because, like for example, if you have 10 terms, add those up, divide by 5. Okay? All right. Next, geometric sequences. So what a geometric sequence is if we take a list of numbers and instead of adding or subtracting the same amount every time, we can multiply or divide by the same amount every time. So in this case, we're multiplying everything by 2 every time. And what we multiply by is denoted by the letter R, the common ratio. So if we wanted to find the 10th term in this sequence, we could say a sub 10 equals the first term, which is 1, times the common ratio R to the 10 minus 1 power, to the 9th power. Now let's say we wanted to add those 10 terms together. We could take the first term, which is 1, times in parentheses 1 minus 2 to the 10th over 1 minus 2. Now we also have infinite geometric sequences. We can't do that with arithmetic because we can't add those, they go on forever. We can't add this geometric sequence because it gets bigger and bigger and bigger, but sometimes geometric sequences get progressively smaller, in which case we could add an infinite number of terms. And we're going to see an example of that in a bit. Okay, we're going to come back to those formulas, so if you need to pause and write them down, that might be a good idea, but let's move on to our first. Oh, before we get into our first example, you may have seen this in a previous class, the summation notation. So if you ever see this capital sigma, it looks like a big pointy E. It's a Greek letter sigma. This means we're going to add up a list of numbers. What do you have on the bottom? I equals 1. It could be I equals 3, I equals 0, doesn't matter. That tells you the starting number. So that means that's going to be your first term. So in this case, it means plug 1 in place of I to start things off. This is going to be your ending number. Now careful, the ending number is not always the number of terms. So if you have a 10 here, it doesn't mean you're going to add 10 numbers. It depends on where you start. And you're going to have some expression in this spot right here. And we'll see an example of that in just a bit. In fact, with this first example, let's take a look at this. Find the sum of what we have here. So we have the summation, j equals 3 to 8. That means we're going to start by plugging 3 into this expression right here. So 5 times 3 is 15. Plus, we say plus because it's a summation. We're going to add these terms together. Now we want to plug in the next number in the sequence. We're going to plug 4 in here. 5 times 4 is 20. Plus, now we plug 5 in here. 5 times 5 is 25. Plus, we plug 6 in here. And then 7. And then 8. We stop after we have plugged 8 in here because of this number right here. Notice that does not mean we have 8 total terms. Instead, it means we stop when we plug the number 8 into this expression, and we get a value of 40. So if we add all these together, we get 165. That's the answer we're looking for. So this is saying, tell me the answer when you add up all these terms, when we plug the numbers from 3 to 8 into this expression. Okay, let's take a look at another like that. So notice, now we're starting by plugging 0 into here. We can start at any value. You'll see 1 a lot, but you can really start anywhere. If you plug 0 in here, 0 plus 5 is 5. Plus, now we'll plug the numbers 0 through 6, so let's plug 1 in there. 1 plus 5 is 6. 2 plus 5 is 7. 3 plus 5 is 8. 4 plus 5 is 9. 5 plus 5 is 10. And 6 plus 5 is 11. And now if we add those numbers together, we get a summation of 56. Okay, so hopefully these summations make sense to you. Let's take a look at another example of this. Oh my goodness, I don't want to do all this work. This means I have to plug the numbers from 1 through 50 into this expression. And if you start this off, if you plug 1 in here, 3 times 1 is 3, minus 1 is 2. Plus, if we plug 2 in here, you get 5. If you plug 3 in here, we'll get 8. If we plug 4 in here, we'll get 11 plus ... because I don't want to do all this work. So here's a case where one of those formulas on one of the previous pages will be handy for us. Notice, it's an arithmetic sequence. So what we always have to determine is it arithmetic or is it geometric, or is there something else going on? Since these terms go up by 3 every time, it is arithmetic. So I'm going to pull the formula that we had on a previous page for the sum of an arithmetic sequence. It looks something like this. The sum of the first n terms equals n divided by 2 times, in parentheses, a sub 1 plus a sub n. Okay, so let's plug in what we know. N is the number of terms. If we start at 1 and go up to 50, there's going to be 50 terms divided by 2. Times, in parentheses, the first term is 2 plus, okay, this means the 50th term. So we have to find the 50th term in this sequence. Now this can be kind of difficult to do. However, if we have summation notation, it's actually relatively easy. Let's just plug 50 in right here. So the 50th term will be 3 times 50 is 150 minus 1 is 149. Okay, so to find that sum, we can take 25 times 151, and if we multiply that together, we'll get 3,775. Now, if you don't trust me, if you don't trust the formula, go ahead and write out all 50 terms, add them up, but I prefer to save a little time and just go right to this answer of 3,775. Okay, let's take a look at a couple more of these. Next, we want to find the sum of this expression here. So again, always start by writing out a few terms. So this is saying plug 1 in place of I. 3 to the 1 minus 1. So it's like 3 to the 0. We know anything to the 0 power is 1. Plus, let's plug 2 in here. 3 to the first is 3. Plus, if we plug 3 in here, we get 3 squared. If we plug 4 in here, we get 3 to the third, etc., etc. Notice this is not an arithmetic sequence. Instead, every term is 3 times as big as the previous term. So this is what's called a geometric sequence. So geometric sequence, if we want to find the sum, we have to use a slightly different formula. So looking back on that previous page, here's what that formula looks like. The sum of the first nth terms equals a sub 1, which is the first term, times in parentheses 1 minus r to the nth power over 1 minus r. So let's see here. The first term is 1 times in parentheses 1 minus r is the common ratio, which in this case is 3, to the nth power. N is the number of terms. Well, if you start at 1 and go up to 20, you're going to have 20 terms over 1 minus r. Now, this can get a little complex to put in your calculator, so let's do what we can here. So 1 times, I'm just going to ignore that 1. We're going to have 1 minus 3 to the 20th power, all divided by negative 2. So if you take care of what's on top, divide by negative 2, you'll get a very large answer, which is going to be about 1.7 times 10 to the 9th. Or if you think about it, that's like 1.7. If we move that point over, that decimal place over 9 places, that's going to give us a relatively large answer of 1.7 billion or so. That's rounded. There's some other stuff going on in here. But just think about this. If we had 20 of these terms added together, we get an answer of about 1.7 billion. That's a pretty big sum. Okay, let's look at one final example. Final example. These ones are kind of confusing for people because if you think about this, this is saying let's add an infinite series of numbers, or infinite sequence. So it's saying let's plug 1 in here, then 2, then 3, then 4, etc., until we have plugged in every single possible integer. Okay, so let's just start this off. If we plug 1 in here, we get 2 to the first is 2, so we get 1 over 2. Plus, if I plug 2 in here, 2 squared is 4, so we get 1 over 4. Plus, if you plug 3 in here, you get 1 over 8. We get 1 over 16. And the doubters out there who are saying, how can we add an infinite set of numbers together? Well, if these numbers get progressively smaller and smaller, what we're adding eventually becomes smaller and smaller, so it should converge on a set number. Okay, so that formula on that previous page said the sum of this infinite geometric sequence. Notice common ratio here. We're not adding the same thing. We're like multiplying every time by a half. So there's your common ratio. So the sum of an infinite geometric sequence is equal to a sub 1, the first term, over 1 minus r, that common ratio. And sometimes you'll see a subscript here, meaning we've got an infinite set of terms. So first term was 1/2 over. Common ratio is also 1/2, 1 minus 1/2. So we end up with 1/2 on top, 1/2 on bottom, meaning if we added this infinite set of fractions together, they would all add up to just 1. That seems kind of strange. Well, let's look at how we can think of this problem. So let's just say we have a rectangle over here, and first I'm going to shade half of that rectangle. So I'll mark that off, shade half of it. Then I'm going to shade a fourth of that rectangle. Then I'm going to shade an eighth of that rectangle. Then I'll shade a 16th of that rectangle, then a 32nd, then a 64th, etc., etc. Now, if you have an infinite number of fractions, well, what's left in this corner that's not shaded becomes infinitely smaller and smaller until, well, if you add these forever and ever on into infinity, there is really nothing left over, which is why this adds up to 1. So it seems like a strange result, and this infinite set of numbers we're adding together, this is one of the big ideas that you're going to see in calculus. So if this idea floors you, don't be surprised, because this is pretty higher level, deeper thinking for us, and we're going to see more and more of this as we lead up to calculus. Okay, so we've got some practice on these sequences and series, so make sure you get some of this practice down before you move on to the next lesson.